part 2. Yesterday we have discussed part 1. So here we have the studies on extraction equilibria, that is extraction of metal chelates, extraction by solvation, extraction by ion pair formation, and synergism. Then factors influencing extraction: pH, molarity of the acids, metal ion concentration, presence of salting out agents, all these things. Then the different approaches for metal ion separation, steeping, pH of the aqueous phase, then criteria for choice of organic phase things. So the studies on extraction equilibria. So extraction equilibria are usually complicated because we have to take into consideration the equilibria existing in both the phases. So one criteria we have to choose the expression. It is verified by observing the effect of variable on the distribution of the metal ion. In this context, the usual methodology which is followed, it is a slope analysis. In slope analysis, the experimental condition chosen is such that the different variables are kept constant except for one. So the first part, the extraction of metal chelates. So as you know, the chelate, that is chelation, so which is the bidentate ligand or multidentate ligand which will form a ring-like structure with metal is known as chelation. So in this classification of extraction system under extraction by compound formation. So compound formation means it will form some complex. So it has been mentioned that chelating agents they form a very important class of extractants. So metal chelates present a type of coordination compounds in which metal ion combines with the polyfunctional base capable of occupying two or more positions of the coordination sphere of the metal ion to form a cyclic compound. So the chelating agent generally which is used, the oxine. Oxine is 8-quinolinol, 8-hydroxyquinoline, which is known as oxine. So this organic compound forms neutral species with a number of metal ions which is insoluble in water but soluble in chloroform or carbon tetrachloride. So if oxine is abbreviated as OX, HOX, then the equilibria, it can be written as the metal ion Mn plus n molecules of HOX is in equilibrium with the oxygen complex MOX whole n, and proton or H plus ion will be released. And another well-known chelating agent which is used in solvent extraction is diphenyl thiocarbazole. Diphenyl thiocarbazone known as dithiazone. So this is the structure of dithiazone. Dithiazone and its complexes with metal ions are insoluble in water but soluble in chloroform and carbon tetrachloride. So we have to do the liquid-liquid phase separation. One organic solvent we have to take in which the metal ion or the complex is soluble, and in aqueous medium it is insoluble. So the list of metals forming chelates includes manganese, iron, cobalt, nickel, copper, zinc, silver, cadmium, tin and lead. So let us study the equilibria. Let us consider that the metal ion with a charge N reacts with an extracting chelating agent to form the metal chelate. When the aqueous phase containing the ligand, that means abbreviated as HR, is brought in contact with the organic phase, the reagent distributes itself in both the phases till the equilibrium is attained. So HR, that is the ligand, so in aqueous phase will be in equilibrium with organic phase. So then what will be the distribution coefficient? So it will be the concentration of HR in organic phase to the concentration of the HR in aqueous phase. So the ligand also dissociates in aqueous phase, which we can write HR is in equilibrium with H plus and R minus. So the dissociation constant of the ligand, that is Ka, as it is acidic, so Ka that can be represented as concentration of H plus in aqueous phase, concentration of R minus in aqueous phase divided by undissociated concentration of HR in aqueous phase. Now, the chelating anion, that is R minus, which will form the chelate with the metal. It reacts with the metal to form the chelate, as shown here. So Mn plus plus Nr minus, Nr minus one negative charge missing here, which will be in equilibrium with Mrn. So the formation constant of this complex, so that is Kf, it will be written by this equation. Concentration of product to product of concentration of reactant. So now the metal chelate formed on equilibrium with the organic phase. Now this is in aqueous phase. Now come to the organic phase. So in organic phase, the aqueous phase and organic phase, they are in equilibrium. Till the equilibrium is attained, the chelate will be formed. So the distribution constant that will be equal to Kdx is given by the concentration of the chelate complex in organic phase to that in aqueous phase. Now in this point, we have to assume that the metal in the aqueous phase predominantly exists as Mn plus. It is in ionic form only, and in the organic phase, it is in complex form. So in other words, these assumptions can be elaborated as the metal ion forms no hydrolysis or anionic complexes in appreciable amount. Second one, the chelate concentration in the aqueous phase is negligible. Okay, because chelate, it is soluble in organic phase. The concentration of the intermediate chelate species is also negligible. There is no intermediate form. The chelate ligand, it will combine with the metal to form the chelate, and there is no intermediate. If these assumptions are taken as valid, then D, the distribution coefficient, that will be equal to concentration of the metal in organic phase to concentration of the metal in aqueous phase, which is equal to Mrn in organic phase divided by Mrn in aqueous phase. So now if you combine this equation 3.1 and 3.8, okay, 3.1 to 3.8, then finally we will get D will be equal to this one. Okay, this equation has been experimentally verified for various metal chelate extraction systems. From the equation, it is evident that D is directly proportional to the Kf, Ka and Kdx, and also the concentration of the ligand HR. So if you interpret the result, this following conclusions can be arrived. In order to have greater extraction, Kf should be as large as possible. This means that more of anion of the ligand must react with the metal to form the extractable complex Mrn. And D is directly proportional to Ka, that is the acidic dissociation constant of the ligand. This means that more is the dissociation of the ligand HR, the more of free R minus will be available for complexation with Mn plus to form the complex. Since D is directly proportional to Kdx, it will mean that the complex should have maximum concentration in the organic phase. In other words, the complex should distribute itself in such that the Mrn total, it will be equal to or it tends to the, that is what will be in the organic phase, because it is soluble in organic and insoluble in aqueous phase. The next consideration is that as D is proportional to HRN plus, it will amount to the fact that more concentration of the ligand should be available in the organic phase for quantitative extraction. Large concentration of the ligand is recommended due to it is recommended to be used. So concentration of ligand, what we have to use, that must be large, so that more complex formation will be there and that will be soluble in the organic phase. Then according to the last equation 3.11, D is inversely proportional to KDR. Because it is written as that KDR to the power minus n. So minus n 1 by KDR to the power n. So as D is inversely proportional to KDR and H plus and concentration, this means that KDR should be small. In order to have small KDR or HR value should be large. In other words, the ligand should have maximum solubility in aqueous phase to have better extraction. So finally, since the extraction is inversely proportional to the hydrogen ion concentration, the extraction is expected to increase with increase in pH. Okay, so basing upon this, so we will rearrange the equation, and if you take the logarithm, so we will get log D equal to log K plus n log HR in organic phase, concentration of HR in organic phase, minus n log concentration of H plus ion in aqueous phase. Okay, or it will be equal to pH, n into pH log minus n log H plus ion concentration means that the pH, so it will plus P. Therefore, it means that the plot of log D versus pH should be a straight line with the slope n and an intercept equal to log K. Okay, this one log K plus n log HR in organic phase. So this is the figure. We show the plot. The slope n gives the number of molecules of the chelating agent involved in neutralizing the charge on the metal. By plotting the data at different pH, the value of both n and K star can be found out. Okay, then the next one will move to the extraction by solvation. So in this case, the neutral inert molecule or complexes by electron donor containing extractants. So a large number of solvent extraction systems are available. So the basic role of a solvating molecule is to increase the solubility of the inorganic species in the organic phase. So if the molecule is more solvated, then solvated in the sense, if it is soluble in organic phase and it is solvated, then large amount of molecule it will be soluble, or solubility will increase if it is solvated. So in other words, the solvating molecules make the extracting species more hydrophobic, thus promoting its transfer to the organic phase. Okay, so as already known, there are two well-known distinct categories of solvating extractions: extractants with oxygen bonded to carbon, already we have discussed, such as ether, alcohol and ketone in introduction chapter. Yesterday we are discussing extractants with the oxygen or sulfur bonded to phosphorus, such as alkyl phosphates and alkyl thiophosphates, not thiophosphates. It may be important to point out here that some of the acidic extractants play a dual role of neutralizing the charge on the metal ion and simultaneously solvating the species. So in this case, you can see one can give an example of Fe3 plus or ferric ion, so which can be extracted. So and
Sir.
extractants like ether, yes, yes, tell, hello,
No, sir. No, ठीक है sir.
हाँ, अरे कौन है?
Sir, please continue, sir. No, sir.
Okay, okay. So we are discussing how Fe3 ferric ion will be extracted. So in this case, the extracting species is postulated as solvated chloroferric acid HFeCl4, and here the C2H5 diethyl ether taken as the solvating agent. So the extraction of Fe3 increases with increasing HCl concentration, reaches to a maximum about 99% at 6 molar HCl, and then starts decreasing with increasing acid concentration. So a decrease in extraction above 6 molar HCl is attributed to the high solubility of ethyl ether in concentrated HCl. So this decrease is not observed up to a much higher acid concentration up to 8 molar. In the case of diisopropyl ether, which has lesser solubility in HCl, okay, if diisopropyl ether will take, then it is less soluble in HCl, so in that case it will be less solvated. So if beta beta dash dichloro diethyl ether is used, no decrease in extraction is observed even at 12 molar HCl. There are other issues involving the organic phase as regards of existence of ion association complex. So the entire system that can be considered as the following steps: formation of FeCl4 minus anion in aqueous phase. So hexahydrated Fe3 plus we have taken, Cl minus from HCl we are giving. So it will be equilibrium with pentahydrated penta aqua, then Fe2 plus and 2Cl minus, and H2O will be released. One molecule of water will be released. Like this, successive addition of chlorine will go on. So 3 molecules of chlorine, 3 water will be released. Then FeH2O whole 2 Cl4 minus. So 4 chlorine will be added. So the different steps may be combined as successive dissociation step if you consider. So hexa aqua Fe3 plus 1 4 Cl minus, so all will combine, K1, K2, K3, K4 will be in equilibrium with the diaqua tetrachloride of iron 3 complex. So the final equilibrium expression that will be K dash, it will be K1 K into K2 into K3 into K4. So I think you know this one in equilibrium in complex coordination chemistry. You have been taught these things: successive dissociation constant. Okay, so it is a product of all the 4 steps what we have discussed here. So K1 into K2 into K3 into K4. So final equation will be this one as shown in 3.20. So this amounts to the fact that at high chloride concentration, the FeCl4 minus is a major species existing in the aqueous phase. In the second step, the formation of solvate. So in this step, it favors extraction in the organic phase. At high acidity, the water activity decreases and the ether activity in the aqueous phase increases. As a result of this, solvent exchange may occur. So that means when acid pH will decrease at high acidity, the water activity will decrease. and ether activity in the aqueous phase, it will increase. So already we have discussed this one in the previous phase, organic, what will happen in, there will be aqueous and organic medium in first section. Today we have already discussed. So what will happen if the water activity will decrease and aqueous phase and the ether activity will increase in aqueous phase. As a result of this, solvent exchange may occur. So this reaction, it will be in equilibrium and equilibrium constant K5 is given. So R2O, so that will be exchanged with water. So this R2O represents the ether molecule. A similar exchange will also take place in hydronium ion. H3O plus ion will be there. So it will be converted to R2OH and H2O will be released. Because hydronium ion, it is a coordination compound of H plus with water. So water will be released and R2O will form complex with H plus. So you will get R2OH plus and water. Next step is the formation of extractable complex. Now we have to look as to how a neutral extractable complex is formed. This has to result as a consequence of formation of an ion association complex with H3O plus and FeH2O2Cl4 minus gives rise to this association complex having equilibrium strength K7. Similarly, if it is the R2OH which has been formed in equation 3.24, that also reacts with the complex to form R2OH plus and Fe R2O whole to Cl4 minus coordination complex. So above two equations can be written in general form as follows. Okay, where S may be water or ether. It is the solvent what we have taken, organic or aqueous. Then the distribution of the reagent and complex. Next step, after having considered the formation of extractable complex, the next step is to look into the distribution of the reagent and complex. So now we'll go for distribution. So general equation we have given KH plus Cl minus. In aqueous will be in equilibrium with that complex in organic phase. Okay, and this complex which has formed HS plus, that means R2OH plus Fe R2O whole to Cl4 minus. So that will be also in equilibrium in aqueous and organic phase. The next step, the polymerization of ion pair in the ether phase. It was indicated earlier in the beginning of discussion on this system that higher iron 3 concentration, the extracting ion pair complex undergoes polymerization in the organic phase. So it may polymerize, N molecules may polymerize to give the polymer, so equilibrium will be established where N varies from 2 to 4 only. It means betamer or tetramer will be formed. Next step is dissociation of the ion pair complex and the reagent in organic phase. At extremely low Fe3 concentrations, the dissociation of extractable complex and the reagent occurs in the either phase, either organic or aqueous. It occurs in the ether phase, that means the organic phase. So this is the dissociation in the organic phase. H plus FeH2Cl4 that may dissociate to HS plus in organic phase plus FeH2Cl4. Similarly, HS plus Cl minus, already we have written that one in equation 3.26. You can see that one. So that is also dissociate to HS plus Cl minus. So now we will consider the overall distribution of iron in its different forms between the organic and aqueous phase. Like our introduction, we have segregate that one, then we have find out the final distribution coefficient D. So same thing we have to apply here. So D, that will be concentration of iron in organic to that in aqueous. So we'll get the 3.31 equation. So that means from this equation it can be seen that the distribution ratio is a complex function of different experimental parameters, and by substituting the relations from previous equation we will get the equation 32. You can see here. So in this equation the two important variables are acidity and the total iron concentration. You can see there from this equation this following conclusion can be drawn. In relatively high iron concentration where polymerization takes place to a significant extent and dissociation is relatively unimportant. So equation 32 it can be simplified because there will be no dissociation. So D what we have seen here, the K7 part we have taken and K11 which is the dissociation part, K12. So everything we have to equalize, so it will be equal to 1. So we will get 1 plus n K10 into Kp into this part. So the first term 1 plus K11 and K12 that is very small, so we have to neglect that one. This simplification results because of the fact that the extent of dissociation is negligible. So K11, K12 are unimportant. Next part, in this region of low concentration where dissociation of complex remains the only significant in organic phase reaction, the terms involving K11 and 12 become important, and those multiplied by K10 become insignificant. So we'll remove the K10 part. So we'll get the equation as in equation number 34. So K11 and 12 are important, and K10 you just see the compare it with equation 32. I remove the K10. So we'll get this equation. So this shows that the extraction increases with decreasing ion concentration, reaching to the value of D equal to Kd into K7 HS plus ion concentration divided by root over of 1 plus K12 into Kd H plus ion concentration into Cl minus ion concentration. So from this equation it is clear that the extraction of Fe3 is favored by increasing acidity. So these equations do not reflect anything on the decreasing of the extraction of Fe3 at very high acidity, which is primarily due to solubility effect. So next we will go to the extraction by ion pair formation. So extraction, here we will discuss two extraction equilibria which are exclusively due to ion pair formation. Extraction of permanganate ion by tetraphenyl arsenium chloride and extraction of anionic metal complex by high molecular weight amine, popularly known as liquid anion exchanger. So we'll discuss this one, extraction of tetraphenyl arsenium permanganate. So that is extraction of permanganate ion by tetraphenyl arsenium chloride. Just 1 minute. Okay, so this tetraphenyl arsenium chloride, it is a water soluble salt. This forms chloroform extractable complexes with anions like permanganate. So the dissociation of the reagent R4AsCl minus R, so R is C6H5, the phenyl. So this is the equation which is in equilibrium with the chloride, dissociated chloride ion in aqueous phase. So this is in aqueous phase. So dissociation constant K will be equal to this one. So the dissociation constant K has a high value because this is highly ionic, so it will dissociate completely. So this is having a very high value. Then formation of ion association complex. In this case, the tetraphenyl arsonium cation combines with permanganate anion to form the complex as shown as per the equation. R4 As plus plus MnO4 minus gives rise to the complex. So Kf, the formation, ion pair formation, association complex formation, Kf, the constant, that is equal to, according to the equation, the value will be like this, and here the value of Kf is small because, and this association complex formation is little bit difficult, so concentration of the association complex is small in comparison to the anion, so therefore Kf value is small. Then third step, distribution of the reagent and the complex. After we have considered the formation of the complex, the next step will be the distribution between the aqueous and organic phase. Once we are considering the distribution of the complex, we'll have to consider the distribution of the reagent also. So distribution of the reagent, so KDR. Hello? Hello?
जी सर
Hello?
हाँ सर कौन सा सर
हाँ ନା ନାଇଁ କିଏ ମାଇକ୍ କିଏ ଅନ୍ କରିଛି ସେଇଆ କହୁଛି ନଏଜ୍ ଆସୁଛି ନା is there anybody else ଆଉ କିଏ ଅଛନ୍ତି କି
ଏବେ ଜଣେ ଜଏନ୍ କରିଥିଲେ କିଏ ଜଣେ
ଆଚ୍ଛା ଆଚ୍ଛା okay I can't see in the mobile na, so because I was sharing the screen, that's why. Okay, anyway, so the distribution of the reagent and the complex. So the distribution of the reagent will be in aqueous and organic phase. The equation will be like this: R plus As plus Cl minus in organic phase to R4 As plus Cl minus in aqueous phase. Then the distribution of the complex Kdx, that will be, the equation will be like this. Then if there will be dimerization, then dimerization of the reagent and the complex in organic phase. So we have to consider that one. Complex will dimerize. So Kp, that means polymerization, Kp we have to give according to this equation. 3.42 will get 3.43. Similarly, next one is the dimerization in organic phase of the manganate, that is of chloride, and this is for manganate. So we'll get the equation like this. So Kp dash. So from the different equilibria, the distribution ratio of permanganate in two phases, that can be described similarly as discussed earlier. So D will be nearly equal to the distribution in MnO4 minus in organic phase to that in aqueous phase. So after equating all these equations, we will get the equation as in 3.45. Now, if the permanganate concentration is very low, in the dimer formation, it may be neglected. Also, the concentration of the ion pair R4S plus MnO4 minus in the aqueous phase is also negligible. So, with these assumptions, the expression of D simplifies to be this one as given in equation 46a, or if put the value which is equal to Kdx into Kf into R4S plus concentration. This means that the distribution ratio of permanganate complex is solely a function of equilibrium concentration of the tetraphenyl arsonium cation R4AS plus. The extraction increases with reagent concentration. Second part, we know that the chloride ion concentration tends to reduce the concentration of tetraphenyl arsonium cation, thus reducing the extraction of the complex. So now distribute the above equation, we will get the final equation as D equal to KDX into KF into K divided by KDR into R4S plus Cl minus in organic to Cl minus in aqueous. Then the second one, this is about the permanganate, then extraction of anionic metal complexes by high molecular weight amine. In the same way, we can discuss this one. This can go through similar manner we have to discuss, and same thing will get the plot taking log D versus concentration of amine, logarithm of concentration amine. So we'll get a straight line, and the value of slope gives the number of amine molecules, that is N. Then next part we will move to the extraction by synergism. Synergism literally means working together. It is a matter of fact that the two extractants work together to increase the extraction by a huge factor. Okay, this word is in solvent extraction we have used this word, and as you can see here, one of the most thoroughly investigated synergistic mixture of extractants is the thionyl trifluoroacetone HTTA and tri-N-butyl phosphate TBP. In its simplest form, the equilibrium we can write as HA, which is equal to, you can say, the thionyl trifluoroacetone HTTA, that is abbreviated as HA, and TBP, tri-N-butyl phosphate, as B. So metal ion reacts with HA. Please move the mic. Whoever is joining, please mute the mic. I'm getting the noise. Hello. Okay. So extraction by synergism led by acid. So MAN plus it reacts with HA. HA is the thionyl trifluoroacetone HCTA. So gives rise the complex. Metal will react with the anionic part, and H plus will be released. And similarly, it will then react with the TBP to produce the complex MAN-BM. That is the synergistic complex. Both will react to produce the complex. So HTTA has been used with different solvating molecules like TBP, TOPO, and TPP, triphenyl phosphate. It was observed that the synergistic effect increases with the increasing basicity of the ester. TOPO, TBP, TPP, all these things. So based on the above discussion, some generalization about the formation of synergistic adduct it can be drawn. So one most important one of the excitant, a ligand or an acid neutralizes the charge on the metal ion, preferably by forming a chelate. The list of ligands is very large. The acid can be organophosphorus or carboxylic acid. Second one, the solvating reagent should displace should displace residual coordinated water from the neutral metal complex, rendering it less hydrophilic. The solvent should not be itself hydrophilic and coordinated less strongly than H plus. Sorry, strongly than HX. The commonly used solventing molecules are organophosphorus compounds and nitrogen containing bases. The maximum coordination number of the metal and the geometry of the ligand should be favorable. Coordination number and geometry of the ligand should be favorable. Okay, so in this manner, the more complexity in the formation of synergistic adduct is being presented by taking extraction equilibrium between zinc and cadmium in chloroform solution of propionic, butyric and valeric acid in presence of amines. So when discussed, so it will exist as the dimer, you can say. In this case, it has been confirmed that there is a formation of salt of the acid with amine. It has also been experimentally confirmed that and known that the acid and the organic phase mostly exist as a dimer. So in such situation, the equilibrium between an aqueous metal ion solution and chloroform solution is of aliphatic monocarboxylic acid and that of amine can be represented by this equation, where N plus is the metal ion, N is the valency of the metal ion, P is the number of amine molecules coordinated, HA is the monomeric acid molecule, B is the amine, X is the number of acid molecules required for solvation, and H2A2O, that is the dimeric acid molecule in organic phase. So in this way, to go on calculating, the equilibrium constant can be given by this equation. Then assuming that the metal ion does not form any other complex in the organic phase and exists only as Mn plus in aqueous phase, then D will be this one, M into the amine. P is the number of amine, so amine into ANHA divided by concentration of Mn plus. So if you substitute the equation in equation 6.3.63, then rearrange, then we will get this one. Taking the logarithm also, we will get log D equal to log Kex. So this equation we will get. So similarly, if we plot, then the slope of log D versus pH. If we plot log D versus pH, the slope at constant acid and amine concentration in organic phase will give the number of protons liberated due to consumption of acid molecules in the complex formation. So from the plot, different plots drawn at different conditions, so which will give the following result. The plot of log D versus pH at constant metal ion, acid and amine concentration for both zinc and cadmium gave straight line with slope near 2. This suggests release of 2 protons by the utilization of 2 acid molecules per metal atom to neutralize the charge of metal ion. Then plot of log D versus log amine, concentration of amine at organic phase at constant metal ion, pH and acid. It also gave a straight line for both the metal ions with all the 3 acids. The slope for aliphatic and heterocyclic amine were 1 and 2 respectively. This suggests in incorporation of one molecule of N-butylamine and dibutylamine and tributylamine and two molecules of beta picoline, pyridine, or quinoline when ether when either of the three acids is used. So, the conclusion. Then, what are the factors that influence the extraction? Factors influencing the extraction. So, there are so many factors, out of which one is the pH, then molarity of the acid, effect of metal ion concentration, then presence of salting out agent, presence of masking agent, concentration of the extractant, and the nature of the diluent. So these are the factors. pH. So this is the relationship. So with equilibrium pH, you can say here pH in the aqueous. So pH when I am discussing, this is relating to aqueous phase. So it is necessarily means the equilibrium pH, that is pH attained after the two phases have been contacted to equilibrium. So graphs show the effect of pH on different metals, percentage extraction with equilibrium pH, extraction of iron, copper, zinc, nickel, and cobalt with Versatic 9, that is the ligand which we are using, which will form the complex. First one with dithiazole, this one with dithiazonates, this is with Versatic 9. Similarly, next we can use this one with THPA from sulfate solution. Then molarity of the acid which we are using here. This graph shows the concentration, H plus concentration with different metal ions, how they will be extracted, percentage extraction versus concentration of HCl. Similarly, another graph is there which shows the percentage of extraction of zinc-2 from HCl solution by variation of 1.1 molar amines in chloroform and benzene. So then effect of metal ion concentration, extraction of mercury from HCl solubility by various 0.1 molar amine in chloroform. Already discussed metal ion concentration. Various metals, effect of metal ion concentration on extraction of titanium, vanadium, iron, copper, zinc. Condition as Phoenix 923 we are using at 0.2 molar, HCl is 5 molar. Then presence of salting out agent, presence of masking agents, EDTA is generally used, commonly used masking agent. The masking agent forms sufficiently strong complexes with interfering metals to prevent their extraction either altogether or at least until the pH is much higher than the value needed for the quantitative extraction of the metal ion of interest. Should be known that very often the desired metal of interest also forms a complex with the masking agent, and a much higher pH is needed for its extraction. So EDTA generally is used as a masking agent. Please mute. Then concentration of the extractant. So then different approaches for metal ion separation. Various approaches are there that we have to discuss. Method of the diluent, stripping pH of the aqueous phase, acid molarity of aqueous phase. You think that you have to go through that one. So different tables are there. pH of the aqueous phase has important role. So acid molarity, then important binary separation involving 3D metal ions from HCl solution using Sinex 92.3 in toluene. These things you just go through it. There's no table, no need to remember. Okay, none of criteria for the choice of organic phase. So what are the different criteria how to choose the organic phase? The component of the organic phase should be immiscible with the aqueous phase. It should have very good stability. This will amount to the fact that the organic phase should be capable of withstanding many recycling operations in a solvent extraction circuit without degeneration. A difference in the density of the contacting phases is essential and should be as great as possible. Low power requirement for pumping and agitating, rapid extraction and settling or dispersion, and high heat and mass transfer rate are corollaries of low viscosity of the organic phase. The interfacial tension should be high for rapid coalescence. The solvent should cause no corrosion difficulties with common materials of construction to reduce the cost of equipment. The solvent should have low toxicity, high boiling and flash point, is mainly avoid environmental pollution and fire hazard, and it should have high metal loading capacity, and it should have it should be easily stripped of the loaded metal. The extractant should have high extraction and regeneration power. The extractant should be selectively to extract one component of a solution in reference to the other. It should have good kinetics of extraction. It should be relatively inexpensive, low cost, and readily available in adequate quantity. The extractant should be highly soluble in aliphatic and aromatic hydrocarbons. So this ends your unit 3. Then some summary, then terminal questions. So that you can do. Okay, just give me 5-minute break. So we'll start the next one, chromatography. Hello.
हाँ सर।
I will start. Just 1 minute. Let me share the screen.
हाँ सर स्टार्ट।
Okay, the second part, that is the third unit, general principles of chromatography. So as the name indicates, chromatography, chrome means color. So basing upon the color in the sense it may be visible region or in UV region. So basing upon the color, we have to separate. So this is one technique. Here you may use the adsorbent or adsorbate, the adsorbing medium, that may be a piece of paper, as in case of paper chromatography, or it may be a column, as in case of column chromatography. And there are some other definition and classifications all also there, like liquid chromatography, gas chromatography, supercritical fluid chromatography, all these things. So we'll discuss one by one here. So definition and classification. Chromatography is a method of separation in which components to be separated are distributed between two phases. One of these is called the stationary phase, and the other is the mobile phase, which moves on the stationary phase in a definite direction. The components of a mixture redistributed themselves between the two phases by a process which may be adsorption, partition, ion exchange, or size exclusion. So these are the process by which the adsorbent will be adsorbed on the adsorbate or the stationary phase. The stationary phase, it can be a solid or a liquid, and the mobile phase is a liquid, gas, or a supercritical fluid. The stationary liquid is held on an inert solid support or coated on the walls of a capillary. The solid, whether it is support or an active material, is held in the form of a.
Hello. Hello.
Hello.
Sir, your class isn't audible. Can you hear me? Is it audible for anyone?
ସାର୍ କିଛି ଶୁଭୁ ନାହିଁ କିଛି ସାର୍।
column coated over a plate or presented as a paper if it is solid as a medium. The latter two types come under the head two-dimensional chromatography. Now coming to the classification, so it can be classified basing upon the following: the shape of the solid support, the nature of the mobile phase, the mechanism responsible for separation. So if you go by shape of the support in chromatography, there will be three-dimensional, that is column, and two-dimensional, that is thin layer and paper chromatography. In two-dimensional chromatography, there will be only only two types of chromatography: thin layer and paper, and all the other forms of chromatography will fall under the head of column chromatography. It is too simple a classification and does not take into consideration the nature of the mobile phase and the process responsible for separation. So the two-dimensional chromatography is operated using a liquid only as the mobile phase. So if you do the classification on the basis of nature of the mobile phase, then there is three types of chromatography taken: liquid, gas, and supercritical fluid chromatography. As already we have given an idea. If we are using liquid as the mobile phase, then it is liquid, gas, and supercritical. The first two are well known, and several advancements have already been made in these two forms of chromatography. But supercritical fluid chromatography, it is a relatively new and does not figure so frequently. So then in case of mechanism responsible for separation, the four distinct types of chromatography such as adsorption chromatography, partition, ion exchange, and size exclusion. So we'll have to separately mention the competing phases, whether it's liquid, gas, or supercritical fluid, whatever may be. So the summing up the classification, then it is liquid chromatography, gas chromatography, and supercritical fluid chromatography, depending upon the mobile phase and chromatography technique. So we'll discuss each one. The first one is your liquid chromatography. The simplest one with liquid as the mobile phase. So it is based upon the partition between the liquid supported on an inert support and the other liquid acting as a mobile phase. This is also known as liquid-liquid partition chromatography. The support holding the liquid can be in the form of three dimensions like a column, or two dimensions like thin layer and paper. In two-dimensional form, the mobile phase can move from top to bottom or bottom to top, and thus known as descending or ascending chromatography. The two types of partition chromatography are also distinguishable on the basis of relative polarities of the mobile and the stationary phase.